So, hello guys. Today we'll start this maximum superposition theorem. Okay, it's in network theory, basic electrical engineering for basic electronics also. So, first of all, what are the conditions where we can apply this maximum superposition theorem? Okay, first thing is that the network must be linear and bilateral. Okay, linear bilateral network. So, linear bilateral network. We can apply this maximum superposition theorem on linear bilateral network. Okay, and what it states, I don't want to write. I just say okay. If load is variable, means in other theorems there is we don't talk about the variable load. Okay, but here we'll talk about variable load. If load is variable, we need to find a condition in which maximum power is absorbed by load. Okay, in if load is variable, load is variable. Okay, we need to find a condition in which the maximum power is absorbed by load. Okay, at load side, there will be maximum power. Okay, you need little bit of knowledge of Thevenin's theorem, but if you don't have also, we can go for this also. Suppose in Thevenin's theorem, what we do, we replace the whole circuit with a voltage source and series connected resistor. Okay, VTH means Thevenin's voltage and RTH, Thevenin's resistance, and this is a variable load, that is RL. Okay, and current following is I. Okay, so this is just representation of the Thevenin's network, this part VTH RTH. But when we talk about maximum superposition theorem, at that time we'll say the load is variable. Okay, so here if we want to calculate current I is equal to VTH by total resistance RTH plus RL. Okay, VTH is Thevenin's voltage. Okay, RTH is Thevenin's resistance when there is no source. Okay, I think I'm assuming that you know. Okay, you know how to calculate this VTH and RTH and all. Okay, so load of what will be load power then now? Load power formula, that is I square R. Okay, so we'll just denote it with PL, I square RL, and we'll just put the value of this, okay, I here. So what it will come? VTH square RL by RTH plus RL. This is load power, means at load side. Load means this RL side, okay? This RL side, where they in question they have asked me to find voltage or current or whatever. Okay, that is load side. So for maximum power, for maximum load power, anytime if they say about find for maximum, that if you know, you always you have to do what derivative. Okay, so we'll do derivative of this. Let's just define dPL by dRL. This will come 0. Okay, so we'll do the derivative dPL by dRL. Or shall we write? Okay, let's go. You can skip some step. VTH square RTH plus RL square minus RL into 2 RTH plus RL divided by RTH plus RL power 4. Okay, so we'll just skip uh, we'll just skip some part of this derivation. Okay, I think you can do derivation, but at last what it will come, I just want to come it directly at that point. Okay, at last it will come, we can write from there, or let's go the second step, not skipping. RTH plus RL by RTH plus RL to the power 4 RTH plus RL minus 2RL. From here, we'll just take this part and we can write RTH plus, sorry, we'll take this part. Okay, not taking that part. RTH plus RL is equal to 0. We can write this. So we can write, sorry, it will come minus. Okay, this will come minus. So we can write RTH is equal to RL. So this is the condition for maximum power. Okay, so now we'll calculate the maximum power. Pmax, for Pmax, okay, let me collect the current first. Okay, for Pmax, what will be the current? VTH by RTH plus RL it was. So now if we just replace RL with RTH from here, so what it becomes? VTH by 2 RTH. Okay, Now P max for load side. Okay, load side I square R always. Okay, I square R L. R here, R L. So VTH square by 4 RTH square. RL we can write RTH here came. So what it will come? VTH square by 4 RTH. This is P max. Okay, this is P max. This is the equation you have to use in your numerical problem. Okay, is it clear? Whenever ask you to calculate the P max, we have to calculate this. And we'll calculate one more thing, that is efficiency. Okay, we'll calculate efficiency. Let me change the color. For that, what we have calculated, maximum power in load, P max at load side, we have calculated just now, VTH square by 4 RTH. And we have calculated the current at maximum power. Okay, I at maximum power, how much it was? VTH by 2 RTH. Okay, so we got the load power. So source power, simple V into I. So here will be VTH into I. Okay, so how much it will come? VTH square by 2 RTH. Okay, VTH into I, calculating multiplying with this current. So now we can calculate efficiency. That's the symbol VTH by 4 RTH, VTH square, actually VTH square by 2 RTH, load side power by source power into 100%, and finally it will come out 50%. Okay, so we are saying maximum power is delivering at load side, but only 50%, only 50% is delivered. Okay, so still there is this percentage is too high compared to these days. Like if you this is actually used mainly in power electronics. So in mainly power electronics, mainly efficiency is nearly 20% to 30%. Okay, normal efficiency is 20 to 30%. So at that condition, if we are getting 50%, so that is higher, that's why we're calling it 50%, and is maximum power is transferring, we are calling it actually. Okay, maybe you can do research, you can come with some other techniques, you can get more than 50% efficiency. Okay, so we'll not do the numerical, we just derive here the maximum superposition theorem. Okay, so what we just go through the ones. What are the conditions? Condition is linear bilateral network. Okay, and one thing is different, that is load here. That is, is there any more color? Okay, that is variable. Okay, variable load here. Here you can see everything is same, almost Thevenin's theorem, like Thevenin's theorem, but load here is variable. Okay, RTH is Thevenin's resistance, VTH is Thevenin's voltage. Okay, we want to write plus minus. We just apply Ohm's law directly for calculating the current. I is equal to VTH by RTH plus RL, V by R. So load power I square RL. This is also one formula. I square R. We are using here. We're just putting the value of I here. So the load power at current side we can calculate here. VTH square by VTH square into RL by RTH plus RL. For maximum power, whenever the anywhere they, if someone asks for maximum power, you have to do derivative. Okay, you have to keep in mind this one. And later, if we do derivative, what it will come out? This, from there we can write this RTH is equal to RL. So at this condition, the maximum power will flow. Means the load power when this RA load power is same with the RTH, Thevenin's resistance. At that time, maximum power will be delivered. Okay. So Pmax we can calculate just by putting the value of RL as RTH. It will come as VTH square by 4 RTH. Okay. Now we'll calculate the efficiency here. So we know at Pmax at load side is this much, VTH square by 4 RTH, and I that is VTH by 2 RTH. From here it is come VTH by this first formula, na? VTH by RTH plus RL. So we are just replacing RL with RTH. Okay, so VTH by 2 RTH come. So we can calculate source power. For source power, V into I. Okay, V into I, voltage into current. So we just did that one, voltage into current. To become VTH square by 2 RTH. Okay, this is the current of voltage VTH, and efficiency, the load side power by source side power into 100, and it will come 50%. Okay, so that's it guys for today. Okay, bye bye. We'll meet you later on with other lecture videos.